So basic quasi-static, we got to stress that. IV curve looks like normal. So you've seen this with CV-RAM and some of the other IV curves. So you're writing to a low resistance, you hit a compliance current on your tool. It's written to some low resistance and it erases, and that's pretty standard. And I call this DC single point curve, but it's not really DC because each one of those DC points is applied for a short period of time. So in this case, they're each applied for 33 milliseconds, but it's one point at a time randomly applied to the device to get this IV curve. Some of the other basic properties of this structure that I described, it's got the usual compliance current dependence, and you see this with all of those devices, CV-RAM, this one, where if you use a different compliance current, your resistance that you write to is lower as you go to higher currents. And what I'm showing here that's labeled erase is the resistance after that write compliance current was applied and the device was written. So you go to erase it, and notice here the 1 milliamp compliance current, it doesn't erase very well in this particular case. This tin selenide stack doesn't like to do that. It will still have a variation in resistances that's reasonable, because you're looking at greater than 10K, but it does permanently change the device. But it does withstand temperature, 23 all the way to 150C. We can keep it at 150C and operate for weeks, and we've done that. And it will go back to room temperature afterwards and look normal. So it's a really temperature hardy stack. Silver's not migrating all over the place, and the materials are really robust. We've got the basic sinusoidal input response that shows the crossing at 0, the nice pinch. And as we increase the frequency from the 0.5 hertz, which is this blue trace, up to 10 kilohertz, which is the black trace, you can see that the lobes flatten out and we get really good, typical generic Memristor response. The other thing that I want to point out with this basic device before we move on from it, it does cycle a lot. And in the lab, we showed it cycling at 23 and 140C for over 1 billion cycles. We only stopped because we had to give up the probe station to someone else. But it was going without any problems, and I'll show you the data for that. But first I want to talk about the test circuit. So the simple test circuit for actually doing the device cycling is different than what we used for this particular test. This was used or collected with a B1500 Agilent parameter analyzer that allowed us to make the measurement directly across the device and measure the current as it was being tested. So there's no load resistor. This is actually the device response. Whereas in this case, we actually used a load resistor, used an oscilloscope, and we measured the voltage across the load as we were doing this measurement, all right? And that's kind of a current limiting thing as well. So the input signal looked like this, arbitrary, but it just seemed to work well, so we used it. And for 23C, you can see we took a measurement every decade. This is the voltage across the load, so remember when it's large, the Memristor has a low resistance. As you write it, Memristor goes low resistance, you erase it, and you can see the spike as the device erases. Memristor goes back to a high resistance state. And over 1 billion cycles, no degradation. And while we're watching this, we keep the scope on persistent mode so we can make sure there's nothing funny happening and it all looked normal. Same thing at 140, we added an extra read pulse just to verify everything was still working well every time. But it's still writing and erasing, and it didn't show any signs of degrading. And we've seen that. We can actually take these devices up to really high temperatures and they'll work fine. They can be pulsed, so you've got your case where you increase your potential on your erase. This is the voltage applied in the black. The erase is really large. It's a 70 nanosecond full width half max pulse applied -3 volts. That's huge. And it erases the device. You can see the current in red shows the state essentially, no current, it's a high resistance. We can write it and the current shows up as a nice low resistance. This is what I call binary operation, because we're using pulse amplitudes that just drive it from one state to another. You know, we're bypassing all those intermediate states and going right there. But if we want to use it in a more analog fashion, you can do that as well. just change your amplitude of your pulses. And in this case, we also changed the pulse width a little bit. So these are a little bit longer. I think they're probably either 500 nanoseconds or 1 microsecond. But what I'm showing is the read pulse, the erase pulse, and the write pulse and read pulses. The current in blue shows only the current through the device during the read to keep things a little simple. And you can see that as we erase it, here's what it initially is. It's a fairly low resistance. We erase it, and we're walking it down and getting to a state where now we're going to write it, and we walk it down, applying these consecutive pulses, and get to another state. And it seems to do that really well. And we're fortunate enough, when I first started at Boise State, we fabricated some devices, and we've been kind of just checking them out every so often. And over the past 11 years, devices, we initially wrote about 20 devices with the DC programming 20 microamp compliance current. And they haven't degraded over 11 years, but that's just a test which may not be practical for anything. And it does show, though, if you did want to use 20 microamp compliance current, you could write your devices for a long time. But I do want to stress that the data retention that you're looking at depends on the programming conditions very much.